2025 A-Level Combined Mathematics Paper 2 Part B question number 13. This question has to do with simple harmonic motion. Now, unlike most of the questions in this paper, question number 13 actually doesn't have any part A's or part B's. The entire question is just one single block of text. Now, this makes the question 13 quite long. But even though it's quite long, you shouldn't get intimidated by its length, because this question is actually quite easy. The question says, two fixed points A and B lie on a smooth horizontal table such that AB length is 16A. One end of a light elastic string S1 of natural length 2A and modulus of elasticity 3 mg is attached to a particle P of mass m, and the other end of S1 is attached to A. Also, one end of a second light elastic string S2 of natural length 4A and modulus of elasticity 4 mg is also attached to P, and the other end of S2 is attached to B, and the particle P is in equilibrium at a point C on the table as shown in the figure. So basically, the particle P is at equilibrium here. On the left side, there's a string connecting A and the point C, or the particle P, and on the other side, there's another string S2 attaching P to B. So these two strings are both under tension in this situation. However, both of them have the same exact tension, meaning that the particle P is going to remain where it is since there is no net force. The particle P is in equilibrium. Now, given this, we are asked to find the lengths of AC and BC, which is quite simple to do. All we need to do is to establish the fact that the two tensions in the two strings are equal and use that to find the position of C relative to A and B. Now, after that, it says, now the particle P is pulled by a distance of 2A towards the point B and released from rest. So basically, from the equilibrium point, we pull it a distance of 2A towards the particle, towards the point rather, B. So when we do that, it's going to be displaced from the equilibrium point. So when we release it from rest, it's going to accelerate back towards the equilibrium point of C. So if it's somewhere over here, which is where this distance is 2A, it's going to accelerate again back towards the point C. So given this, we're asked to show that the equation of motion of P is given by x double dot plus omega squared times x minus 6A equals 0, where the distance AP is what we call x, and omega is some value greater than 0, which is a constant to be determined. So basically, given this equation, we need to solve for this equation, and when we get the equation into this format, we can find out what omega is, and we need to find out what omega is. So after that, it says, by taking capital X equals simple x minus 6A, we will show that x double dot plus omega squared times x equals 0, which can be done by simply substituting capital X into this equation right here. And then we have to state the period of this simple harmonic motion, which is basically the time it takes for the motion to repeat itself. So after that, it says, using the formula x dot squared equals omega squared times c squared minus x squared, we have to find the amplitude c of the oscillation and the maximum speed of P during this motion. So the amplitude c is basically the maximum displacement from the equilibrium point that the particle gets, and then the maximum speed of P during the motion is going to be the maximum speed which occurs when the particle crosses the equilibrium point. So after that, it says, at the first instant when P reaches C during this motion, the string S2 is cut. So basically, when we start from over here and accelerate in this direction, when we do this and move like this, and eventually the particle P gets back to the equilibrium point C, then the string S2, which was like this, is cut, meaning now the only force experienced by P is coming from S1. So then, suddenly, at the point C when S2 is cut, the acceleration of P is going to change. It's going to suddenly start accelerating towards A again. And as it does this, what we're going to have to do is to figure out the motion. So it says, let D be the point on AC such that AD length is equal to 2A as shown in the figure. So given this, we are asked to show that the equation of the motion of P from C to D is given by y double dot plus omega 1 squared times y equals 0, where the length dp is equal to y and omega 1 is some value greater than 0, which is a constant to be determined once again. So once again, we need to solve for this equation, and when we do this, we will find what the value of omega 1 is equal to. So after this, it says, show that the amplitude of this simple harmonic motion is the square root of 68/3 times A, and find the total time elapsed from the instant when P was set in motion until it reaches the point A. So for that last part, we need to consider the entire motion from the point here where particle P was released, from where this distance was 2A, we release it, it accelerates, it reaches the point C, at which point we cut the string, it accelerates again, and as it goes, it eventually gets to this point, which is a distance of 2a from the point A, which at that point what's going to happen is that the tension in the string S1 becomes 0 since it's at its natural length, and at that point it's going to continue under its own velocity, under its own momentum until it reaches the point A. So for that entire motion from this point until it accelerates to this point here, and then the string S2 is cut and accelerates again to this point and moves under constant velocity, this entire motion is what we're talking about when we talk about the elapsed time. So let's start off with this question. The first thing we're going to do is to find the equilibrium point C by finding the lengths AC and BC. To do this, what we're going to do is to consider the situation, draw the diagram, consider some lengths, and find the tensions, and show that when the tensions are equal, the length is going to be a particular value which we can use to find AC and BC. So if the point A is over here and the point B is over here, and let's suppose the point C with the particle P is somewhere over here, then the length AC is going to be the total length of the string S1, and the length BC is going to be the total length of the string S2. Now, since the natural length of the string S1 is 2a and S2 is 4a, any extension beyond that is going to be the only thing contributing to tension. Now, since both of these strings have to be under tension, since the sum of the total lengths, total natural length is 2a plus 4a, which is 6a, but the total length from the A to B is 16a, since both of these strings must be under tension due to that, we can say that a certain length of the total length AC is going to be the natural length, let's say this length here, 2a, and similarly, a certain length of the total length BC is going to be the natural length of the string S2, which is 4a, and the remaining lengths, which is this length and this length, are the extensions. So if I just mark that out, this length is going to be the extension of the string S1, and this length is going to be the extension of the string S2. Now let's suppose that the extension of the string S1 is, say, x0. Now given this, since the total distance here is 16a, this distance is 2a, this distance is 4a, and this distance is x0, this distance must be 16a minus 2a minus 4a minus x0, which is going to be 16a minus 6a minus x0, or 10a minus x0. So therefore, if the extension of the string S1 is x0, the extension of the string S2 must be 10a minus x0. Now given this, we can find that if the tension here in the string S1 is, say, T1 and the string here is T2, then for equilibrium we can say for equilibrium we must have that T1 is equal to T2, which I'm going to call equation number 1. Now we can find formula for T1 and T2 based on the following formula. If you have a string with tension T, extension E, natural length L, and modulus of velocity lambda, then T is going to be equal to E over L times lambda. So tension is equal to extension over natural length times the modulus of elasticity. Now applying that for T1 and T2, we can write T1 equals and T2 equals. For T1, the extension is x0, the natural length is 2a, and the modulus of elasticity is 3 mg. So therefore we have x0 over here, x0 divided by 2a times 3 mg, and for T2, the extension is 10a minus x0, the natural length is 4a, and the modulus of elasticity is 4 mg as given up here. So substituting those in, we have 10a minus x0 divided by 4a times 4 mg. We're going to call this equation number 2, and we're going to call this equation number 3. So now what we're going to do is to substitute 2 and 3 into 1 and basically make the left hand side here this thing and the right hand side here this thing. So doing so, if we go down and write using 1, 2 and 3, we're going to substitute and we're going to get on the left hand side this thing, which is x0 divided by 2a times 3 mg, x0 divided by 2a times 3 mg equal to, on the right side we're going to get this thing, which is 10a minus x0 divided by 4a times 4 mg. 10a minus x0 divided by 4a times 4 mg. Now in the next step we can cancel out the 4 mg, or the mg, not 4 mg, mg and mg. We can cancel out the 4 here for this 4, and we can cancel out the divide by a here for this divide by a, leaving us with, on the left hand side, when all of it cancels, x0 divided by 2 times 3, and on the right side we're going to have 10a minus x0, since the 4 cancels for this 4, a cancels for this a, and mg cancels for this mg. So then if we multiply both sides by 2, we're going to have 3x0 equal to, this thing multiplied by 2 is going to be 20a minus 2x0. Taking the x0 to the other side, we have 5x0 equals 20a, and that means that x0 is equal to 20 over 5a, which is going to be 4a. So x0 is equal to 4a. Now going up, what we wanted in the question was to find the lengths of AC and BC. Now according to this diagram, AC is this total length, which is 2a plus x0, and BC is this total length, which is 4a plus 10a minus x0. So going down, we can say AC is equal to 2a plus x0, which is equal to 2a plus 4a, which is 6a. So AC is equal to 6a. BC is equal to 10a minus x0 plus 4a, which is equal to 10a minus 4a plus 4a, which is equal to 10a. And therefore, BC is equal to 10a. Now we could have also said that AC plus BC is equal to AB, which is 16a, and then just subtracted the 6 here. But I wanted to do it this way. So anyway, we have found the lengths AC and BC in the equilibrium point, where the equilibrium point is the point C, where AC is equal to 6a and BC is equal to 10a. Now in the next part of the question, we displace the particle from that equilibrium point C by a distance of 2a. It says we displace it by a distance of 2a towards B. So from this point we pull it over here where this distance is 2a. So then we release it from rest, and we have to show that the equation of motion of P is given by x double dot plus omega squared times x minus 6a equals 0, where AP is the distance x. So the distance from A to the point P is going to be x. So to solve this, what we're going to do is to go down here, draw out the situation, and then we're going to apply F equals ma in order to solve it. So if I just draw this out, we have the point A on the left here. This is A. B is over here. C is over here. And from C, we displace it a certain distance. Initially, it's going to be 2a. So we'll write the initial point 2a. The point P is over here. And the distance from A to P, which is going to be this distance right here, is the distance that we call x. So x is in this direction. From A to P, this is x. And then if that is x, then the other distance from the other side from B to P is going to be equal to the total distance of 16a minus the distance x. Now, both of these strings are under tension, but if you consider natural length, the natural length of the string AP, which is S1, is going to be 2a, and the natural length of the string BP, which is S2, is 4a, and due to that, the actual extensions which cause the forces here are actually not the entire length, but rather this length and this length. Now considering those two lengths, this length is going to be the total length x from here to here minus the length 2a, so it's going to be x minus 2a, and this length here is going to be the total extension here, total length here rather, of 16a minus x minus the natural length, which is going to be 4a, so it's going to be 16a minus x minus 4a, which is going to be 12a minus x. So the extension of the string S1 is x minus 2a, and the extension of the string S2 is 12a minus x. Now given this, at this point the particle P is going to experience a tension in this direction and this direction. Let's say the tension of S1 is T1 and the tension of S2 is T2. Now given this, we can find the values of T1 and T2. So for T1, T1's extension is going to be x minus 2a, and then we have divided by the natural length of 2a and multiplied by the modulus of elasticity of 3mg. As for T2, T2's extension is going to be 12a minus x, natural length is 4a, and we are going to multiply by 4mg because that's the modulus of elasticity. Now, what I'm going to do here is to take these two and apply F equals ma. To apply F equals ma, I need an acceleration. So since x is taken from A to P and it accelerates or increases in this direction, I'm going to take the acceleration in this direction as x double dot. Now I could take it in the leftward direction as well, since actually that's the actual direction in which the particle P is going to accelerate. But if I was doing that in the direction from P to A, x would be decreasing. So if we take P towards A, x is going to decrease, which means that the acceleration is actually a deceleration or a reduction, a negative acceleration. So to avoid this, I'll just say that I take x double dot in the positive direction, and then the sign is eventually going to come out as negative. So I'm going to take x double dot to be the acceleration in the direction in which x is increasing, and then we're going to apply F equals ma using the forces T2, T1 and the acceleration of x double dot. So applying that, if I say applying F equals ma, we're going to apply F equals ma for the particle p in the positive direction of x, which is the rightward direction, and doing so for the forces in the positive direction we get T2 minus T1, so we have T2 minus T1, T2 minus T1, and on the right side we have ma, and a is x double dot, so we have mx double dot. Now I'm going to call this equation over here 3, actually 4, I'm going to call this equation over here 5, and we're going to call this equation over here, let's say 6. So we're going to combine 4, 5 and 6, and if I do that I'm going to get T2 minus T1, which is going to be 12a minus x divided by 4a, 12a minus x divided by 4a times 4mg minus x minus 2a divided by 2a times 3mg, x minus 2a divided by 2a times 3mg equal to m x double dot. Now here I can see I can immediately cancel the m from here, here and here, leaving us with x double dot on the right hand side and a bunch of stuff on the left hand side. Now if I start simplifying, I'm going to get x double dot equal to, and simplifying all of this, we are going to have, if we take, we can cancel this 4 for 4, leaving us with 12a minus x divided by 4, divided by a times g minus, and here we're going to have x minus 2a divided by 2a times 3g. Now what I'm going to do is I'm going to factor out the g divided by a's, and I'm going to, actually we can be a little clever here. If we take a 2 out as well, then we can multiply this by 2, and then we're going to get x double dot is equal to g over 2a, and then we're going to have on the inside, this is going to become 24a minus 2x minus x minus minus becomes plus 2a and times 3g. So this whole thing needs to be multiplied by 3, and then that's going to be that. So now if we simplify this down, we're going to get x double dot equal to g over 2a multiplied by, we're going to get 24a, and this 2a times 3 is going to give us plus 6a minus 2x minus 3x, which is going to become x double dot equal to g over 2a times 30a minus 5x. And we can see if we factor out a 5 here, we're going to get 6a minus x, and in the question we had x minus 6a, so that's probably what we want to do. So if we do that, if we take the x minus 6a by taking the 5 out, what we're going to get is x double dot equal to 5g over 2a times 6a minus x, and we take that to the other side, we're going to get x double dot plus 5g over 2a times x minus 6a equals 0, and this is the form that we wanted, but we wanted it as x double dot plus omega squared times x minus 6a equals 0. So we can say that this is the case where omega is equal to, and here omega squared must be equal to 5g over 2a, and since 5g over 2a is a positive number, we can write directly that omega is equal to the square root of 5g over 2a. And hence we have solved for omega. Omega is the square root of 5g over 2a, and we have found the equation that we wanted, x double dot plus omega squared times x minus 6a equals 0. And hence we have solved that part of the question. Now after this, the question asks us to take a new variable, and it says by taking capital X equals simple x minus 6a to show that x double dot plus omega squared times x equals 0, and state the period of the simple harmonic motion, and then using the formula capital X dot squared equals omega squared times c squared minus capital X squared, find the amplitude c and the maximum speed p during this motion. Now to start this, what we need to do is to take capital X equals simple x minus 6a. So we're going to say let capital X equal to simple x minus 6a. Now given this, we can see in this formula we can directly substitute x minus 6a for capital X here. But in this formula we also have simple x double dot, which we need to substitute with some formula of capital X. So in order to do that, what I have to do is to take this relationship between capital X and simple x and take the derivative of both sides. So if we take the derivative of both sides, on the left hand side taking the derivative with respect to time, we're going to have capital X dot. On the right side we're going to have simple x dot plus the derivative of negative 6a, which is going to be 0, so plus 0, which I'm going to erase and just have capital X dot equals simple x dot. Now taking the derivative one more time, we can see we're going to get capital X double dot on the left hand side, and the right hand side we're going to get simple x double dot. So therefore simple x double dot is directly equal to capital X double dot, and we already have the relationship that capital X is equal to simple x minus 6a, meaning that using these we can substitute into this expression to get that capital X double dot plus omega squared times capital X is equal to 0, where omega is equal to the square root of 5g over 2a. So now we have done our substitution. Now when we do the substitution, we can see we have the form of the second derivative of a variable plus omega squared times that variable equaling 0. This is the principal equation of simple harmonic motion, and due to this we can say that this omega is actually the angular velocity corresponding to the simple harmonic motion that we have here. So due to that, from the above, what we wanted to find was the period, and the period of this oscillation is going to be equal to 2 pi divided by the angular velocity. So therefore we're going to have the period of oscillation equal to 2 pi divided by the angular velocity, which is 2 pi divided by omega, which is 2 pi divided by the square root of 5g divided by 2a, which is equal to 2 pi times the square root of 2a over 5g, which I'm actually going to leave like that as my final answer. So therefore the period of oscillation here is 2 pi times the square root of 2a over 5g. Now after that, it said using the formula x dot squared, capital X dot squared equals omega squared times c squared minus x squared, find the amplitude of c and the maximum speed of p during this motion. So for the first part, what we can do is to apply capital X dot squared equals omega squared times c squared minus capital X squared, and what we can do is to apply this to a particular situation where we know both the value of capital X and the value of capital X dot. Now considering the situation that we have, we were initially at this point somewhere over here to the right side of the equilibrium point with a distance of 2a, and at this particular point our velocity was 0 and the distance of simple x was 6a plus 2a, which is 8a. So therefore we can say when simple x was equal to 8a, which was the initial point to which we pulled the particle p before releasing it, we had x dot equal to 0. Now from the conversion of x, capital X and simple x, we know that this is correspondent to capital X equals this 8a minus 6a, which is 2a, and capital X dot equals 0, since capital X dot was equal to simple x dot as we found up here. So due to that, we can substitute these two into this expression over here, and by doing that we can find the value of c. So substituting, we can say substituting, we get 0 squared on the left hand side equal to omega squared, which is 5g over 2a times c squared minus 2a squared. Now we actually don't really need to go any further than this. We can just directly say that c is equal to 2a. What I'll actually simplify this, if I simplify, we're going to get c squared minus 2a squared, 2a whole thing squared equal to 0, whole thing squared equal to 0, which means that c squared is equal to 4a squared, which means that c is equal to the square root of 4a squared, which is 2a, since this whole thing is positive and c is also positive. So therefore c is equal to 2a, meaning that the amplitude of our oscillation is 2a. Now given this, the next thing we were asked to find was the maximum velocity of the particle. So the maximum velocity or maximum value of x dot, as we know from theory, is going to be equal to omega times the amplitude, or c times omega. Now the reason we know this is because, considering the equation that we have, if x is anything other than 0, then we can see c squared minus x squared is going to be less than c squared. So considering this, we can see the maximum value is going to occur when capital X is equal to 0, and therefore when that happens, we are going to have x dot squared equals omega squared times c squared, meaning that x dot equals omega times c is the maximum value we are going to get. So therefore, if we substitute into this, we are going to have omega, which is the square root of 5g over 2a, times c, which is 2a. So therefore, we have the square root of 1 over square root 2a times 2, which is going to be the 2a square root times 5g square root, which is going to be 10ag square root. So the square root of 10ag is the maximum value of x dot, and that occurs when simple x is equal to 8a, or when simple x is equal to 6a rather, or we could say capital X is equal to 0. So when capital X is equal to 0, the maximum velocity is achieved at square root of 10 ag. Now I could also say here that this happens at capital X equals 0. Now I'm going to write this here just because this is going to be useful for the next part of the question. Now I of course know this in advance, but you yourself can come back and write this later if you feel that it's required. Now the reason I say it's required is because when this happens, when capital X is equal to 0, as in when the particle returns to the point C, what we're going to do in the question is to cut the string S2. So when the particle returns to the equilibrium point C, as they say, when P reaches C during the motion, the string S2 is cut. So at this point, at point C, we have the acceleration of 0 and the velocity of square root of 10 ag, but then suddenly the string S2 is cut, meaning that the only string left at this point is going to be this string, which is the S1 string, and it's under tension, meaning that we're going to start accelerating in the leftward direction at the point C. So now the next thing we have to do is to consider that motion. It says let D be the point on AC such that AD is equal to 2A as shown in the figure, and show that the equation of motion of P from C to D is given by y double dot plus omega 1 squared times y equals 0, where dp is equal to y and omega 1 is a positive constant to be determined. So for this one again, we're going to use the same exact approach that we used here, only now instead of our initial velocity being 0, we know that at the point C, when we cut the string, the initial velocity is equal to this value of root 10 ag, and this is exactly why I put capital X equals 0 as the location at which this happens, because we can use that to start our new motion when S2 is cut using this value of velocity of root 10 ag. So if we go down and consider that, I'll go to, actually we can start here where there's a little bit of space. So if we start with this space and draw the diagram, we have a line of motion. On one side of the line we have the point A over here. Somewhere over here we have the point D, where AD is equal to 2A, and then we have some point here where the particle P is at. We have the initial point C. At point C we had a velocity of the square root of 10 ag, and then we could also say the distance here AC is equal to 6A, and then this distance D to P is the distance which we call Y. So now in this string from A to P, there is a tension which we will call, for example, we cannot use T1 since we already used T1, so we will say something like T1 dash. So T1 dash is the tension that we have here, and the acceleration of Y I'm going to put in the positive direction like I did for X, and I'm going to call it Y double dot. Now Y is of course not accelerating in this direction, it's accelerating in this direction, but since I don't want to write a negative Y double dot, I'm going to write Y double dot in the positive direction, and then I'm going to eventually get a negative value for that. So writing it like this, I can apply F equals ma to this situation and find a similar equation to what I did previously. So to do that, I need to find T1 dash in terms of Y, which I'm going to do now. I'm going to write T1 dash equals, and if you take a look here, since 2A is equal to natural length, the value Y is actually equal to the extension of the string S1. And due to that, when we're substituting here, we can say that T1 dash is directly equal to the extension Y divided by natural length of 2A times modulus velocity of 3 mg, and that's going to be equation number, we're up to 7, so number 7. And then applying F equals ma, if you go to the next page, applying F equals ma, if we apply F equals ma in this direction to the particle P, we're going to get only negative T1 dash, so negative T1 dash, and then that equals ma, which is going to be my double dot. Now from this, we'll call this equation number 8. If we combine 7 and 8, what we're going to get is that negative y over 2a times 3mg, negative y over 2a times 3mg is equal to my double dot. Rearranging, cutting the m, we can see we're going to get y double dot plus 3g over 2a times y, 3g over 2a times y equals 0. Now what we wanted is a pattern of y double dot plus omega 1 squared times y equals 0. So we can say this is the case where omega 1 is equal to the square root of 3g over 2a. Once again, we can write this directly since omega is positive and 3g over 2a is also positive. So therefore, omega 1 is also found. Omega 1 is equal to the square root of 3g over 2a, and we have y double dot plus omega 1 squared times y equals 0. Now given this, they asked us to find the show that the amplitude of this simple harmonic motion is equal to the square root of 68 over 3 times a, and then we are asked to find the total time elapsed from the instant when p was set in motion until it reaches the point a. So first off, for the amplitude, what we can do is to use the fact that this is already in the form of certain variable second derivative plus omega squared times times that variable equals 0, which we can then directly use to say that this implies that y dot is going to be equal to omega 1 squared, y dot squared is equal to omega 1 squared times c, let's say c1 squared minus y squared. Now using this, we can say that at the point when x is equal to 0, capital X equals 0, the velocity is equal to the square root of 10 ag, and then we can establish a relationship between y and capital X in order to find the corresponding value of y. So we can see here y is this length, which is x minus 2a. So y is x minus 2a, so we can write that y, simple y, is equal to x minus 2a, and capital X was equal to x minus 6a. So therefore, combining these two, we can see x is equal to y plus 2a, and capital X is equal to simple x is equal to capital X plus 6a. So y plus 2a equals capital X plus 6a, meaning that y is equal to capital X plus 4a. Now using this, if we take the second derivative, actually we don't need the second derivative, we can only take the first derivative because we don't actually need the second derivative here. We can just take the first derivative and that's going to be enough. So from this we can see that y dot is equal to x dot, meaning that in this equation we can see that when capital X was equal to 0, capital X dot was equal to the square root of 10 ag, meaning that the corresponding value of y is 4a, and at that point y dot was also equal to the square root of 10 ag. Now using these two values, we can substitute them into here in order to find the amplitude. Now I should probably also say where c1 is the new amplitude, just for clarity. So now given this, we can substitute and say, substituting on the left hand side we have y dot squared, which is going to be 10 ag, so we have 10 ag equals, on the right hand side we're going to have omega 1 squared, which is going to be 3g over 2a, so we have 3g over 2a times c1 squared minus y squared, so we have c1 squared minus 4a whole thing squared. Now simplifying this down, we can see if we take the 2a to the other side, we have 10a times 2a, which is going to be 20a squared, equals, we have 3 times c1 squared, so 3 c1 squared, and then minus 4a squared is going to be 16a squared, so we have minus 3 times 4a squared is going to be minus 3 times 16 is going to be 48, minus 48 a squared. Taking everything to one side, we have 3c1 squared equals 68 a squared, meaning that c1 squared is equal to 68 over 3 a squared, and since c1 and a are both positive, we can see that c1 is going to be equal to the square root of 68 over 3 a, and that is our final answer for that part of the question. Now the last final part of the question is asking us to find the total time elapsed. It's asking us to find the total time elapsed. Find the total time elapsed from the instant when p was set in motion until it reaches the point A. So here what we need to find is the total sum of all of the times that we have in this question. Now, considering all of the motions that happened here, initially we were at a point over here. If this point is C, this point is A, and this point is B, we were somewhere over here where this distance is 2a, and in this case both strings S1 and S2 were intact, and we are accelerating in this direction. And as we were accelerating, when we got to the point C, this is one time. When we pass C, we cut the string, meaning that now we are under a different acceleration. We accelerated and we got to this point, but at this point, remember, since the string's natural length is 2a, at the point when the distance here is 2a, we're going to lose that tension, meaning that after that point, from this point to this point is one time, and then after that point we're only going to be going with our momentum. So after the point when this distance is equal to 2a, we're only going to be going on the momentum. So we have 3 times to measure: this time, this time, and this time. This time, the first time, is going to be the time at which we have both strings and we are moving from the point here where x is equal to 8a until x equals 6a, and after that the second time is when x is equal to 6a until x equals 2a, and the last time is from x equals 2a until x equals 0. So if I write that down, from the motion we're going to let t1 be the time from AP distance equals 8a, which is the starting point, until AP distance equals 6a, which is the point at which we cut the string, and then t2 be the time similarly from, and then AP in this case is 6a, until we lose tension in the string, which is going to be AP equals 2a, and then t3 be the time from AP equals 2a until AP equals 0. So now we've clearly defined the 3 times at which points we have 3 different motions occurring. T1 and T2 occur under simple harmonic motion, and T3 is occurring just under momentum, where we're just moving under the momentum that we gained from the entire oscillation. So considering T1, T2, T3, if we try to do T1 first, for T1 we started at AP equals 8a, which was actually at a maximum amplitude, was at amplitude of 2a, and AP equals 6a was at the center of oscillation, since it was in fact at the equilibrium point. So due to this, we moved from an amplitude until we were at the center of oscillation. Now considering the circle and considering the harmonic motion that we have here, if this is the amplitude and this is the center, then what we did here is basically move 90 degrees along our imaginary circle of simple harmonic motion. And due to this, we covered only 1/4 of the entire period, or 2 pi divided by 4, or pi by 2 radians of our entire rotation. And due to that, we can say that the time taken, time t1, is equal to that angle that we turned to, which was pi by 2 divided by the omega, which in this case was just omega as we defined above, which is going to be equal to pi by 2 divided by the total period, total angular velocity, which was the square root of 5g over 2a, which is going to be equal to pi by 2 times the square root of 2a over 5g. Now we could simplify this further, but I'm going to leave it as that, and I'm going to move to the next time. So for the next time, from AP equals 6a until AP equals 2a, if we consider what we had, the total amplitude that we had in that situation was this value, square root of 68 over 3 times a, and in that case, if we consider the motion, we started with a value of AP equals 6a, which if you consider AP equals x, that means that y was equal to 6a minus 2a, which is 4a. So we started from y equals 4a, and we're going to end at y equals 0. So we're moving from y equals 4a to y equals 0. Now considering the circular motion in the circular path that we're traveling on, if we just draw a little circle to demonstrate, we have this turn here, and out of this turn, if the entire radius of this circle is equal to the square root of 68 over 3 times a, then we were at a point such that the horizontal distance here was equal to 4a, and we moved until the horizontal distance was equal to 0. So considering that situation, the angle that we turn through is the angle in between this line that I just drew and the vertical upward line. So this angle here is the angle we turn through. So therefore, under the new angular velocity, which was omega 1, the total angle that we turn through here was omega 1 times t2. So this angle here is omega 1 t2, and we can find the value of omega 1 t2 based on the other values that we have. Now here, since the hypotenuse here is also going to be equal to the radius of 68 over 3 times a, and this value here is 4a, and this angle here is opposite of that side, we can say that the angle here, omega 1 t2, is the sine inverse of 4a over square root of 68 over 3a, which you can simplify down to 4 over the square root of 68 over 3, or 4 times the square root of 3 over 68. So therefore, omega 1 t2 is equal to the sine inverse of 4 times the square root of 3 over 68. Now, after this, what we can do, we know omega 1, we found omega 1 up here somewhere. Omega 1 is equal to square root of 3g over 2a, so we can substitute that in. Substituting that in, we can get t2 is equal to the square root of 2a over 3g multiplied by the sine inverse, we can just directly write it, multiplied by the sine inverse of 4 times the square root of 3 over 68, and that is going to be the value of t2. Now finally, for t3, to find the value of t3, we need to find the maximum velocity achieved by the particle as it leaves. So considering that, that's going to happen at y equals 0, and considering y equals 0 and the equation that we got, c1 is equal to square root of 68 over 3a, meaning that maximum velocity y dot is equal to the amplitude, which is c1, times the omega, which is omega 1, which is going to be equal to the square root of 68 over 3 times a, multiplied by the square root of 3g over 2a, multiplied by the square root of 3g over 2a. And if you multiply these two, we can see the square root of the 3 and square root of 1 over 3 cancel out, leaving us with the square root of 68g over 2a, which we can simplify down and cancel the 2a. 68 divided by 2 is 34, so we have 34 times the square root of a times 1 over is going to be 34a. So it's going to be square root of 34a times g, 34ag. So square root of 34ag is going to be the velocity achieved at the end when y is equal to 0. So therefore, from y equals 0 until y equals negative 2, which is the final point, we are moving under just momentum. So from AP equals 2a until AP equals 0, we move at a constant velocity. Since there's no acceleration now, the string becomes slack. Constant velocity of y dot here, which is equal to the square root of 34ag. So square root of 34ag. Now finally we can say that therefore, if you consider v s equals ut plus half at squared, then the distance we have to cover, which is 2a, is equal to ut, which is square root of 34ag times t3 plus half times 0 times t3 squared. Simplifying this down, we can see that t3 is equal to 2a divided by the square root of 34ag, which we can simplify down to t3 equal to square root of 4a divided by 34g, which is equal to, we can take a 2 out, which is going to give us 17 here, 2a over 17g. Now, the total time elapsed is the sum of these 3 times. So therefore, we can say finally the total time, we can say maybe therefore total time elapsed is equal to t1 plus t2 plus t3, and we can finally be done with this question by writing down the final values of t1, t2 and t3 and adding them together. So it's equal to, t1 up here was equal to, where's t1? T1 is equal to pi by 2 times root 2a over 3g, so 5g. 2a over 5g. Pi by 2 times square root of 2a over 5g, pi by 2 square root of 2a over 5g plus t2 was equal to this thing. I'm actually going to copy the whole thing. I don't want to write it again. This whole thing, the square root of 2a over 3g times the sine inverse of 4 times root 3 over 68 plus t3, which is equal to the square root of 2a over 17g, square root of 2a over 17g. Now finally I'm just going to see if there's anything I can factorize out here. I can factorize a 2a over g square root out of all of these, so I'm actually going to do that. I'm going to factorize out a 2a over g root, and we're going to be left with pi by 2 over root 5. We can write 1 over root 5 pi by 2, 1 over root 5 pi by 2 plus over here we're going to have 1 over root 3 sine inverse of 4 root 3 over 68 plus, and here if we factor out that, we're going to be left with 1 over root 17, and that is going to be our final answer for this question. So that's all. That is quite a long question, but it was not all that complicated. Like, we didn't have to apply any interesting theories or not so obvious logic here. We just had to follow the pattern, know that what we need to do, and know all of the formulas for simple harmonic motion, and doing all of that, we could easily find all of the answers in this question. Now this question is of course quite long, and the reason for that is, again, as I keep saying, because this question doesn't have any parts. So don't be intimidated by this question. It's actually quite easy. It did take quite a long time because I had to explain a lot of things. However, this question is worthwhile, and I would highly recommend that you try it if you are interested. So now finally, let's discuss the marks awarded for this question. So at the start, when you're solving for the initial equilibrium position, when you get T1 and T2's formulae and you substitute and get this equation right here, you get 10 marks. And then when you solve it and get x0 equals 4a, which is the initial extension of the string S1 equals 4a, you get 5 marks. Now conversely, you might have taken the initial extension of the string S2, in which case you should get 6a, and that will give you 5 marks. Now using that, when you substitute and you get AC equals 6a and BC equals 10a as your two answers for AC and BC, you get 5 marks and 5 marks for both of them. Now after that, when you then consider displacement that we do and try to find the equation of the motion, when you get T1's equation you get 5 marks and T2's equation you get 5 marks in this dynamic situation. And after that, when you substitute them and get the correct F equals ma equation, you get 5 marks for that. Now after this, when you solve it, simplify down, and you get to the format that you wanted, which is x double dot plus something times x minus 6a equals 0, you get 10 marks. When you identify that this something should be omega squared, in which case omega is going to be equal to the square root of 5g over 2a, you get another 5 marks. Now after this, they asked you to do a substitution of capital X equals simple x minus 6a. When you do that, you take the derivative twice and you say that capital X double dot equals simple x double dot, you get 5 marks. When you substitute those things into this formula right here, you get 5 marks. And then when you use this to find the period of oscillation to be equal to this, when you either write 2 pi by omega directly or you substitute and write the final answer, you get 5 marks. For some reason here, they'll accept 2 pi by omega as a correct answer instead of having to substitute and simplify all the way down. So anyway, after that, when you then use this formula and use the knowledge that at x equals 8a, x dot equals 0, meaning that at capital X equals 2a, x dot equals 0, you get 5 marks. When you substitute those values in to get that the amplitude c is equal to 2a, you get 5 marks. And then after that, when you find that the maximum velocity achieved by the particle p, x dot maximum, is equal to omega c, is equal to root 10 ag, for all of that work, you get 10 marks. Now after this, when we cut the string when the particle p reaches that point, as in capital X equals 0, and we consider the situation at that point, when you draw all the diagrams, get the correct values, get t dash, t1 dash, here the tension in the string, and then using that, when you apply F equals ma correctly, for all of that you get 5 marks. When you simplify down to get this equation of the form y double dot plus omega 1 squared times y equals 0, and you get that omega 1 is equal to the square root of 3g over 2a, you get 5 marks. Now after this, when you simplify down using the other equation here, and you get that capital X equals 0 implies that y is equal to 4a, and at the point when capital X equals 0, y equals 4a, x dot capital X dot is equal to root 10 ag, meaning that y dot is also going to be equal to root 10 ag, you get 5 marks for relating that. When you use this relation to then substitute, and you get this equation of y dot squared and all of that, substitute in, you get 5 marks for substituting, and simplifying down to get C1, the second amplitude, equals square root of 68/3 times A, you get another 5 marks. Now after this, when you then consider the times involved, for finding time t1, you get 5 marks, and then for drawing the diagram for time t2, you get 5 marks, and finding time t2, you get another 5 marks. And then when you realize that after t2's motion, as in after the string becomes slack at the point when x equals 2a, you need to find the maximum velocity, and then the rest of the motion is going to be under momentum for that velocity. When you find the maximum velocity equal to square root of 34 ag, you get 5 marks, and then when you apply s equals ut to find the time t3, you get another 5 marks, and finally, when you add all 3 times to get the total time like this, when you write some formula that looks like this, you get another 5 marks. And that is going to be all for this question. Now I know it was quite a long question, but as I said, I would recommend that you try it because it's not all that complicated. You just need to apply the same exact theory again and again and again. And you can actually breeze through this question and you can kind of flow through this question without really thinking too much about it, since all of it is exactly the same. So that's going to be all for this video. I hope you enjoyed. If you have any feedback, post them in comments down below. Thank you for watching, and goodbye.